Okay. Now, next topic in memory management is speeding up the paging. So we have discussed the paging scheme, which is implemented using virtual memory concept, right? Now, we are familiar with virtual memory and paging. But whenever, so we have discussed theory, but now let us see implementation point of view, right? So if any paging system, whenever your system is using paging scheme, then there are two major issues that must be addressed, right? So first issue in paging is what? The mapping from virtual address to physical address must be fast, because at each and every memory reference we require mapping from virtual to physical address, right? So this mapping must be fast. If it is slow, then there is no meaning, right? So it is necessary to make one, two, or sometimes more page table references per instruction. And if an instruction execution takes say 1 nanosecond, the page table search must be done in under zero point 0.2 nanosecond. So this we required mapping between virtual to physical mapping, right? And for that we require to searching in page table, right? So this searching must be fast, then and then our conversion or mapping will be fast, right? So that is the first issue, that mapping must be fast. And how we can make it fast, so we'll see solution later on, right? And second issue is, if the virtual address space is large, the page table will be large. So as we have discussed, for each and every page, or you can say in page table, per page one entry is there, right? So per page one entry in page table. So if your virtual address space is large and page size suppose is small, so number of entries will be large, right? So we need to accommodate large page table in main memory, in physical memory. So that is the problem. So what we'll try to decrease or minimize our page table. And again, advantage will be, if page table is small, then searching will be fast. So these are the two issues. So we'll discuss solution for each and every issue one by one. So first of all, we'll address. Let us try to make mapping from virtual address to physical address fast. So for that, we are having solution, that is true translation look aside buffer, or you can say it is sometimes called TLB or associative memory. This is the solution for first issue. First issue was mapping must be fast, virtual address to physical address, right? It is taking time. Why? Because we are having large page table, because we are having large virtual address space. So per page one entry in page table, so we required more searching time, right? Because number of entries are more, then we required more searching time. So instead of going for whole page table search, we can manage a small data structure or small hardware, equip our computer with a small hardware device that is used for mapping virtual address to physical address. And instead of going to the page table, so that device or hardware is called TLB, or translation look aside buffer, or you can say associative memory. And you can refer the example of TLB in Tenenbaum. That figure is not given over here, right? So this is the example of Tenenbaum. So translation look at aside buffers, or you can say associative memory, is made up of it is we can say it is usually inside MMU. So TLB is inside MMU. MMU is what? Memory Management Unit, and consists of small number of entries, not more than 64, right? Minimum 8 and maximum 64. So searching will be fast. If number of entries are less, then searching will be fast. So if searching is fast, then mapping will be fast, right? So instead of going to search in page table, what we are doing, we are maintaining TLB, and if we require, then and then we will go for a table search. Okay, so now let us try to understand functioning of TLB. So each entry contains information about one page. So that information may be like page is valid or not. Valid means page is currently available in memory or not. Virtual page number, right? Then suppose here we have taken page number like 140, 20, 130, 129, 19, 21, 860 and 861. So this is the page numbers, virtual page numbers currently used, right? So this page virtual page number and 140 is mapped with page frame number 31. So page frame field indicates particular virtual page is mapped with which particular page frame, right? And another field is modified, and then protection of modified. We have already discussed all these fields, right, in page table entry. So TLB contains this many informations. So using these informations, we can simply easily map our virtual page with page frame if page number is available in TLB, right? So how it functions, let us understand. It is usually inside MMU and consists of small number of entries. Each entry contains the information about one page. So per page information will be like virtual page, bit, protection code, and physical page frame in which page is located, valid entry fields, and like so on. Okay. So when a virtual address is presented to MMU for translation, so in paging scheme, what we are doing, CPU generated addresses, that is virtual address, is sent to the MMU for translation, right? And the hardware first checks, means TLB first checks to see if it virtual page number is present by comparing it to all the entries. Means current virtual address present in particular page, and that page number is present in TLB. If yes, then simply if a valid match is found, the access does not violate the protection bits, then page frame is taken directly from the TLB without going to the table search, right? So first of all, we'll try to find particular page number is available in TLB. If yes, then simply will take page frame number mapped with that page and directly translate our virtual address into physical address, and there is no table search, page table search is required, so mapping will be fast. But suppose because we are having small number of entries in TLB, so it may happen particular page is not available, so there will be a page fault, right? So when a virtual page is not available in TLB, the MMU detects a miss, or you can say page fault, and does an ordinary page table lookup, right? So we'll go for page table search. So it is like cache memory, right? So if page is not available in cache, then we'll go for disk search, right? Or main memory, and if it is not available in main memory, then we'll go for disk search. Same way, if page number is not available in TLB, translation look aside buffer, then and then we will go for page table search, right? And page table having large number of entries. Why? Because for each and every page there will be a entry in page table. Okay. And see it what it does, then it evicts one of the entry from the TLB and replace it with the page table entry just looked up. Current recently used page will be put means entry for that page will be put in TLB, and less used page will be evicted from TLB for future use, right? So it's all about TLB. So TLB is the solution for a first issue, that is mapping must be fast, right? Now another issue is what? Page size, sorry, page table size. So if our page table size is more, then what will be the problem is uh, a full it will occupy memory, main memory, right? Why problem is what? Whenever suppose you are executing your process, right? And for that process there is one its own virtual address space and its own page table, right? And page table must be in main memory. So if page table size is more, then will occupy more memory, physical memory. So already we are having less amount of physical memory, right? So a full time page table in main memory we cannot afford, right? So we required some solution for that. So now solution is maybe what? Okay, how can we reduce the size of our page table, right? So as we have discussed in solution 1, TLBs can be used to speed up virtual address to physical address. The translation is over the original page table in memory scheme, but that is not the only problem we have to tackle. Another problem is how to deal with very large virtual address spaces. So whenever our virtual address space is large, your page table will be large because per page one entry is there, right? So we'll discuss two way of dealing with that. So if we are having large page table, then we are having two solutions: multi-level page tables and inverted page tables. So we'll discuss these two topics. Multi-level page tables. We'll try to understand multi-level page table. One of the solution for second issue with figure 3.16, in which we have 32-bit virtual address that is partitioned into 10-bit PT1 field, 10 bits for PT2 field, and 12 bits offset field. Since offsets are 12 bits because pages are size 4 KB, and there are about total 2 raised to 20 of them. The secret to the multi-level page table method is to avoid keeping all the page tables in memory all the time. In particular, those that are not needed should not be kept around. So we'll keep only those tables, or we can say fields, in main memory which is currently required. So this is the main concept of multi-level page table. Level may be any. In this example we have taken two level page table. As per requirement we'll go for 3, 4 or more levels, but complication will be there, right? So in this example you can refer this figure. Here we can see two level page table, so multi-level page table, in which we have taken example of two level page tables. So in figure 3.16b, we see how the two level page table works in this example. On the left, We have the top level page table with 1024 entries. Means at first level we are having 1024 entries, that is 2 raised to 10. Means first 10-bit PT1 field. Corresponding to the 10-bit PT1 field, when a virtual address is presented to the MMU, it first extract the PT1 field and use this values as an index into the top level page table. Each of these 1024 entries represent 4M because the entire 4 gigabyte virtual address space has been chopped into chunks of 4096 bytes. The PT2 field is now used as an index into the selected second level page table to find the page frame number for the page itself. Example, as an example, consider 32-bit virtual address. Suppose our virtual address is 4206596, which is 12292 bytes into the data. This virtual address corresponds to PT1 equals to 1 and PT2 equals to 2 and offset 4. The MMU first used PT1 to index into top level page table and obtained entry 1, which corresponds to address 4M to 8M. It then used PT2 to index into the second level page table, just found and extract entry 3, which corresponds to address 12288216383 within its 4M chunk. Absolute address 4206592 to 4210687. This entry contains the page frame number of page containing virtual address 4206596. If the page in memory, the page frame number taken from the second level page table is combined with offset 4 to construct the physical address. This address is simply put on the bus and sent to the memory. So it's all about multi-level page table. Now next solution for second issue is inverted page table. So we have discussed multi-level page table, but for 32-bit virtual address space, the multi-level page table works reasonably well, right? There is no issue. However, as 64-bit computers becomes more common, the situation changes drastically. If the address space is now 2 raised to 64 bytes with 4 KB pages, we need a page table with 2 raised to 52 entries. If each entry is of 8 bytes, the page table is over 30 million gigabytes. 30 million gigabytes just for page table is not a good idea. So here a multi-level page table will not work for 64-bit page or you can say virtual address space. So we require different solution, and one such solution is the inverted page tables. In this design, there is one entry per page frame in real memory. So till now we have discussed in page table per page entry is there. But now what the concept of inverted page table suggests, instead of page table, instead of page entry, here will make per page frame entry, right? So rather than one entry per page of virtual address space, will keep per page frame entry. For example, with 64-bit virtual address spaces and 4 KB page and 1 GB of frame, An inverted page table only required 262144, means 2 raised to 18 entries. Instead of 2 raised to 52, we required only 2 raised to 18 entries. Why? Because we are making per page frame entry in inverted page table. The entry keeps track of which process or virtual page is located in the page frame. Although inverted page tables save vast amount of space, at least when virtual address space is much larger than the physical memory. They have a serious downside. Virtual to physical translation becomes much harder. This is the disadvantage. Otherwise, if virtual address space is far larger, or you can say much larger than physical memory, then inverted page table is the good idea. Okay, so again it is having its own disadvantage, but this is the solution for second issue. Okay, and now in next lecture we'll discuss, this is the example, you can refer figure 3.17 for inverted page table. Okay, and in next lecture we'll start page replacement algorithm, which is the most important part of this memory management. We'll discuss in next lecture.